What is the Heliosphere? A new mission could unravel the mysteries of this complex cosmic environment. Surrounding our solar system is a natural and enigmatic cosmic shield called the Heliosphere, and a new mission has launched to help astronomers better understand it. Created by the solar wind, a constant flow of charged particles that stream away from the sun, the heliosphere acts as an enormous bubble that protects the planets in our solar system from cosmic radiation permeating the Milky Way, our home galaxy. In addition to Earth's protective magnetic field, the heliosphere plays a major role in why life is possible on our planet and how it perhaps once existed on others, such as Mars. Over half a dozen missions have contributed to how astronomers understand the heliosphere, and two enduring spacecraft, the Voyager probes, have collected key data after exiting the heliosphere to explore interstellar space. But the new IMAP, or Interstellar Mapping and Acceleration Probe mission, is designed to investigate how the Sun forms its solar wind and how that solar wind interacts with interstellar space at the boundary of the heliosphere, which begins at a range 3 times the distance between Earth and Pluto, according to NASA. The spacecraft's 10 instruments will also fill gaps in the existing map of the heliosphere, pieced together from data collected by previous missions, and help further explain how the heliosphere largely shields our solar system from damaging cosmic rays, the most highly energetic particles in the universe. Along with 2 other space weather missions that lifted off aboard the same rocket on Wednesday, IMAP will help scientists better predict when solar storms unleashed by the sun could affect our planet. When aimed at Earth, harsh radiation from the storms, also known as space weather, can pose risks to astronauts on the International Space Station, as well as interfere with communications, the electric power grid, navigation, and radio and satellite operations. Dr. Joe Westlake, director of NASA's Heliophysics Division, said this next set of missions is the ultimate cosmic carpool. They will provide unprecedented insight into space weather. Every human on Earth, as well as nearly every system involved in space exploration and human needs, is affected by space weather. Mapping the heliosphere. The heliosphere was first theorized by multiple scientists investigating the concept of cosmic rays and the solar wind in the late 1950s, according to NASA. They believed the sun provided a web of magnetic fields and solar wind that created a boundary surrounding Earth and the rest of the solar system. Mariner 2, the first successful mission to another planet that performed a flyby of Venus in 1962, also was the first to measure the solar wind, proving its existence. Direct measurements taken by the Pioneer 10 and 11 missions in the 1970s, as well as the Voyager probes, provided further proof of the heliosphere. Scientists are eager to know what the boundaries of the heliosphere look like, something that the Voyager probes have offered tantalizing glimpses of in the past. They are the only 2 spacecraft to cross the heliosphere. Voyager 1 reached the heliosphere boundary in 2012, while the slower Voyager 2 crossed the boundary in 2018, providing snapshots in 2 specific locations. The information collected by these probes is helping scientists learn about the heliosphere's comet-like shape. The IBEX, or Interstellar Boundary Explorer satellite, has been mapping the heliosphere since launching in 2008. But IMAP can explore and map the boundaries of the heliosphere like never before because it has instruments with faster imaging that are capable of 30 times higher resolution. Once it reaches an orbit about 1.6 million kilometers from Earth in about 3 months, IMAP will also capture observations of the solar wind in real time and measure particles that travel from the sun, study the heliosphere's boundary between 9.7 billion to 14.5 billion kilometers away, and even collect data from interstellar space. Predominantly, IMAP will measure energetic neutral atoms called ENAs, or uncharged particles that form when an energetic charged ion collides with a slow-moving neutral atom. The process that forms these particles, found wherever there is plasma or charged gas in space, also occurs throughout the heliosphere and along its boundary. IMAP will rely on tracking these particles to create a more complete map of the heliosphere, according to NASA. The particles travel in a straight line, unaffected by magnetic fields because they are not charged, so IMAP can collect ENAs near Earth and trace them to their origins, like the otherwise invisible boundaries of the heliosphere. Dr. David McComas, IMAP's principal investigator and astrophysicist at Princeton University, said IMAP is going to make incredibly detailed pictures that will evolve over time of that interaction region. It will be able to understand what the shielding is, how the shielding works, and what it looks like. Our solar system is not alone in having something like a heliosphere, and bright astrospheres have been spotted around other stars. Monitoring space weather. The Carruthers Geocorona Observatory is a small satellite that will be dedicated to observing the exosphere, or Earth's outermost atmospheric layer. The Carruthers mission will capture images of the region's faint ultraviolet glow, called the geocorona, to help answer questions about the exosphere's shape, size, and density. The mission is named after Dr. George Carruthers, who developed an ultraviolet camera as the first moon-based observatory that was placed during the Apollo 16 mission. The camera, still in place in the Descartes Highland region on the Moon, photographed Earth in ultraviolet light and captured the first image of the exosphere in 1972. The mission will measure changes and the effects of space weather once it reaches Earth, given that the exosphere marks a transitional boundary between Earth and space. Meanwhile, the SFWO-L1 mission is intended to act as a solar storm detector, providing early warnings to protect astronauts in low Earth orbit and satellites that provide critical communications on Earth. It's a tool that will be even more necessary as astronauts venture farther into deep space. The satellite's compact coronagraph telescope will monitor the sun for activity and measure the solar wind, providing a constant stream of data to NOAA's Space Weather Prediction Center. Images of solar storms taken by the satellite can be sent to the center within 30 minutes, while other current missions, like NASA and the European Space Agency's Solar and Heliospheric Observatory, launched in 1995, can take up to 8 hours.